so it's the probability of y being yn given the past stuff here times the probability that xn equals x prime given the past. I just don't have to write down all that again. All right. And so that's the product of the sensor dynamics. That's what's given to you. You know?
The sensor dynamics depends on u as well.
That's right, and they're here.
Here.
Yes. I mean, I didn't put all this stuff. Those dots are here. That's right. You could see I was having trouble fitting all that stuff in. But all the stuff there is all here. Okay, so this sensor dynamics, the probability that I observe one depends on whether it's at the top of the hill or not, and it depends on un-1, whether I'm driving or not.
You also use a notation also on the notes where you have q.
Yeah.
Little q.
That's little q of y n given x n and un-1 times the probability n-1 of going from x to x prime. There you go.
And q is the sensor PMF.
That's what I was using for the sensor PMF before. This, yeah. Okay, and so that's why it's so easy to run this. It's nothing. It's one line. It's a couple lines of code. Yeah. Yeah, it really isn't bad. And unfortunately, it's too much information. I mean, the example's not great, because you'll find that the maximum posteriori estimator, the map estimator, is so damn good. It's just like, it's right 90% of the time. So the stupid, naive, optimistic policy works really well. I'm still. Yeah, the map estimate is the maximum likelihood. My maximum a posteriori.
Yeah, but is that what?
No, that's the conditional distribution.
Yeah, it's just
Yeah. X map
would be the maximum.
Yeah.
The maximum.
Yeah, it's the argmax. Yeah.
So
and for that, you don't even have to normalize.
Is that the one that you want, or are you looking for the conditional mean?
The conditional mean you couldn't use, right? So when I talked about the optimistic policy, the optimistic policy, one of the ones I decided, one of the policies to try is UN is equal to phi star of x hat and map. That's what we called optimistic last lecture, which fails miserably for a bandit problem. You can't put a conditional mean there because it wouldn't be defined. This phi star is only valid in 3 values: top of the hill, middle, bottom. Well, the conditional mean would take on continuous values between.
So we couldn't do a plug and play policy.
No, without the conditional mean, but you can with the map. Yeah.
That's weird, because I remember when you first introduced the information,
Yeah.
the whole belief state, information state stuff.
Yeah.
It was just like, so how do you get your policy? You just take like the maximum belief, and you're like, no, that's map, that's something else, and I became very confused.
Oh no, but that's just one dumb policy. I mean, another one is I've told you that the cost is a function of u in the belief state, so you could do that as well. You could do the That's a greedy policy. And might work great. Who knows? Probably not. And so my other suggestion is a one-step improvement of that in a way. That yeah. Is there?
Definition of bn plus 1 dot of x.
Oh, is there a typo where?
It's bn plus 1 dot of x prime.
Oh, is it missing prime here? Yeah. Oh no. Oh, wait here. Yeah.
Left hand side is bn plus 1 dot of x prime.
Oh yeah. Thank you. No. Oh right. Oh, it's because of this jerk here. Anyway, that's better anyway. So, okay. All right. I want you all to do this, you know.
Sorry, one more thing. So it, like you said, you couldn't do a plug and play with the minimum, with the expected, conditional expected value estimator, because it's not necessarily going to give us a value on the state. It can give us like things that are not within the state.
Yeah.
And so, just because we can't do, it's a better word for like plug and play.
No, we're calling this the optimistic policy.
The optimistic, yeah. Since we can't do the optimistic policy.
No, we can. The optimistic is great.
Well, with the condition.
Oh, but that doesn't make any sense.
Value in there doesn't make sense.
Yeah.
But like, it is possible to derive a minimum like mean squared estimator, like full policy, like that isn't say like here we're just plugging in our x hat into whatever phi star is. Is it possible to like have a policy that is minimum in the mean squared like?
No, you can compute the optimal policy. You really could do it. I mean, if you can compute that suggestion I gave, value iteration for this is not that big a deal. And so there is a absolute optimal policy, and it is given by UN optimal is equal to some phi star as a function of the beliefs and yn. And the problem is, of course, that if you want to do value iteration, the value function is a function on beliefs, which are continuous values, which, yes, it lives in R2. R3, but it's really 2. Because the entry sum to 1. It lives in a two-dimensional subspace. And so, but you can, you can bin, you can quantize.
Did we ever talk about how you force the value iteration to constrain the belief to only be valid?
Oh, just make it. It's a function of two variables. Just write that the third value is 1 minus the sum of the first two. It's no big deal. Yeah,
okay.
It's no big deal. You just keep that. You don't. Yeah.
Okay.
Right.
And that should be more optimal than the.
Yeah, I don't know how much. I haven't seen it yet. Yeah.
Okay, I see. I think I understand what you're begging for now.
Yeah. I'm tempted to do it myself. Just keep so many things to do, and I have brain damage from allergies. It's just.
Why the emphasis on value iteration as opposed to policy?
Well, the thing is that I have a feeling when you bin belief state, you're probably going to get like 1,000 states. Maybe like a 30 by 30 grid or something.
What should be the
That's what I was saying, like 30 by 30 maybe. We're going from 0 to 1. Each entry of B can take on values between 0 and 1 because it's a probability value. And it seems like 1 over 10 seems a bit maybe too fat. Maybe 1 over 30 would be okay. And then there are two of them though. There's two triangles because it's the information. Yeah. Sorry, y can take on two values, and that y could be 0, I get a triangle. Y could be 1, I get a triangle. And so if I did take a 30 by 30 grid, I'd get 1,000 states because it's a triangle. And 1,000, invert 1,000 by 30 is a matrix, takes a microsecond in MATLAB. Yeah, it's going to be a really ill condition, so it might be. I don't know. It'd be fun to. What the hell? What the hell would be?
But also we can take 3 states and sum it equal to 1.
That's why I'm saying it's only 2. That's what I'm saying. Yeah, B might be in a 3-dimensional vector, but the last component is 1 minus the sum of the first two. So this lives in a. That's why I say it lives in a triangle, a 2-dimensional triangle. Yeah, it was called the simplex. Yeah, And at 3:30 this morning, I got an email from this guy who had actually done, had actually coded this. And, it's pretty cool. Let's see, what time is it? Did you guys understand my intuition about what the policy should look like, the optimal policy? There's the triangles, the drawings there.
It's a little tricky to interpret if you want to describe it.
Yeah, it's just that the information state, which is equal to the belief state and the observation, it belongs to a union of two triangles. So the way in my picture, I indicated that these corners mean that I know I'm in the bottom. And we all know that if I know with 100% certainty I'm in the bottom, I will drive. And so it's pretty intuitive that there'll be some region, a decision region, if I'm close enough to the bound. If I'm sure enough that I'm here, then I will drive. So what you're doing now is a version of this. When you're doing this, your decision region is looking at I don't know. I'm having trouble doing this. Optimistic, I have a belief. I'm saying which chord am I closest to? That's the definition of this argmax. All right? Which am I closest to? So right now you're looking at a decision region that's pretty fat. Now I'll bet you the optimal policy might be a little bit more conservative. You might not, you might be less likely to drive. I bet you'll drive a little less when you're not optimistic. And then our terminology optimistic will be validated. All right? When I'm doing this, I'm saying which chord am I most closest to? Yeah. I'm glad I said that. Is that clear? It's not clear? No, why is that not clear? No.
I don't see why the y t equals 1 case is a triangle.
No, I'm saying that by definition, this decision so remember, if you go back at the solutions to the homework, you only drive if this is equal to the bottom, if you're at the bottom of the hill. Okay? So this decision region says that if x hat map is bottom of the hill, I will drive, otherwise I won't. Okay? Now if I look at this belief space world, that's the region where x map equals 1. Because that's the region where I'm closest to that corner. That corner corresponds to the probably 1 I'm at the bottom. That corner in my notes was a probability at the top was 1, and that corner is a probability I'm in the middle is 1.
So the triangle, the space inside the triangle are all possible belief state values, because
yeah, those are all possible B of t. Yeah.
It's 2 values, and then the third one is like 1 minus the other, so that's why it's.
That's right.
Okay. So if we get a certain belief state, saying the argmax of that is picking the state that is closest to the belief state maximizes. So if we're closest to one corner of the triangle, we get that value, and then we use our policy, our old options.
That's right. And with this policy, it's those polyhedral regions where I'll say yes, I'll drive, and otherwise I won't. Yeah. And I'll bet they're too big.
Can you tell me something, because I don't have a copy of home right now. We can only observe 2 out of the 3 states.
We only observe in that homework problem. If you're at the top of the hill, there's a positive probability that you will know you're at the top of the hill, and you're completely blindfolded on the middle or in the bottom. There's no information. You're just totally closing your ears and you've got your blindfolds on.
Okay.
Yeah. Which is a bit artificial. It was pointed out that if you're at the top of the hill, you're getting energy. You know you're getting energy. So that's a bit strange. So it's a bit of a phony problem in a way.
In value iteration, what row will you assume that probability for that signal, that sensor to show 1?
Oh, whatever. I gave you a half, right? I mean, I gave you numbers there.
So
yeah.
In value iteration, you use the same.
Yeah.
It's either 1 or 0, right? With probability half.
Yeah. I mean, I'm not sure what you're saying. So there's a transition. There's a very simple transition law for this 2-dimensional process. It really isn't bad. And you go and run it. Yeah. And you'd have to go and you have to work in a grid. You have to,
Okay, so with some probability that you're at the top of the hill, and then 1 minus that tells you you're either at the middle or the bottom. And then you do the estimation with like the regular probabilities that we have from the previous homeworks to try to discern whether.
No. I mean, to construct this filter, you're given the data I've given you. Yeah. Right. And once you have the filter and you're running it, you can compute this at each time instant, and that corresponds to a decision region in this information state. Yeah. Yeah. And with the, we'll get something else with other policies. You get like this thing here. That's also piecewise linear because it's a minimum of linear functions. So you'll get a different jaggedy thing for this. Yeah.
So one of the things that's kind of interesting, however, with the truly optimal policy where we just find a 5-star that takes in the information state and tells us what to do, without the optimistic policy, the one you wrote over there to the right. Is there a way to describe what kind of state estimation it's doing?
No. It's always the same state estimation. It's always here.
Well, it always gets that distribution, but it's not necessarily just taking the argmax and then.
No. It'll be a decision. Yes, theorem. It is a polyhedral like this. It turns out that you can prove that the optimal policy will just look just like this, but it'll be a different region. It might have 4 faces, not just 2. It might be a smaller region, but it's going to be some convex polyhedral region containing this point that you can prove.
So your map is basically just which vertex am I closest to? You're saying the optimal one.
The optimal one will be some maybe smaller polyhedral region. Okay. I don't know. It might be bigger. I don't know. I haven't worked it out. That's why I wish that I had more energy and time. I wish I could show it to you.
Is that suppose for some reason the truly optimal policy was to just use the optimistic policy, if that was possible, then how would we be able to tell? Because
you'd look at the dynamic programming equations and see if they get solved. You could hope to solve the DP equations. Not very likely. Yeah, no. Whether there's an optimality gap or not, you'd have to hope that you could solve the dynamic programming equations, but then forget it. Yeah, never mind. You'd still have value iteration. You'd have to solve Poisson's equation for the. Yeah.
We're just going to simulate which one's better.
Yeah, that's all you can do. That's all you can do, unless one of you has some brilliant idea that's, Okay. Now, but this is really great because. Given that I know all this structure, why are we making this so complicated? Why can't we, look at a class of decision regions and optimize over them? Why can't I decide my decision region will have 2 faces, but could be any angle, move them around. I'd have a 2-dimensional problem to solve that I should be able to solve. Damn it!
Why not?
Why not? So that's the remainder of this course. The remainder of this course is that we have structure for a problem, and we'd like to use it, and then have some way to try to get the best solution in that class. And this is still a young field, and so a lot of things are still kind of flaky. But I can say without any arrogance that I'm the best person to teach this to you, because I might not be the most experienced in applying this, to make money in Wall Street, but I think I know more about what works and doesn't than anybody alive. I'll say that on camera. And I know that just from reading the literature so much, and it's been affirmed. So Aditya and I have had sleepless nights for the last 6 months or longer trying to read the literature, and we found so many mistakes and so many things that people all assume are true and are false, just clearly false. And so you've got to be careful to read in this area. All right, and it'll be fun. I'm trying to come up with a homework problem where we can play with that, where we can do what I just suggested. So. So, okay, so what I just described to you just now, that I have some family of policies, I want to figure out which one is best. That's called an actor-critic approach. So let's think about average cost optimal control. I've got a family of policies. And by the way, again, I'm going to be going back and forth between writing U of t and U sub t. I apologize. It's just, you know, just t means time, okay? And just stick with me on that. And I would love to, my dream is to minimize overall theta of the summation over x and u Yeah. So, you know, basically with this policy, I will have a steady state distribution, and then I can compute the steady state mean, which I would call eta theta, using the notation I've used before. And you could try steepest descent. Now, that scares me a bit because this function might be shaped like this. You know, it might be incredibly non-convex, number one. And also, it involves trying to compute this monster over and over and over again. Okay? But this monster is an expectation. You know? So, you know, note that eta theta is equal to an expectation with respect to this sort of theta policy. Its gradient, we might have time to show, is another expectation. This squiggling here refers to the fact that it's a bit complex. It involves Poisson's equation again. Everything does. Okay. And we could try to find a solution to that expectation being 0. Okay, the squiggle just means I don't want to write it down. All right. Now, what am I getting at here is that in trying to do what I talked about a moment ago, what I end up getting is the expectation of something. This might depend on theta as well. I'll put that in there as well. I have an expectation of something is equal to 0. All right? And so that's maybe something we'd like to try to solve. You all happy? Now that looks scary as hell, and we probably won't get to it because this, in terms of immature areas, to me this seems like the most immature. You know, unfortunately, it's like the dream, because very often you have intuition about the structure of policy. You know, it's some threshold form, like we just saw. But this tends to be so non-convex. You know, it's just sort of ugly. You know, and so I don't know. But I can easily give you algorithms, but it's just I don't have as much confidence when they'll work. It's some crazy function, which I'm not going to. Yeah, I only made it crazy. I could have written F, but I'm trying to emphasize that it's something fairly complicated. It involves, you know, some funny terms.
It's some function of C?
A function of X and U. No, it's derived from Poisson's equation and taking gradients and all sorts of things. Yeah. Yeah. Okay, so that's one. And two are rooted in dynamic programming equations. And I'm not going to use this temporal difference language. Forget it. I mean, I will say that, you know, I'll just say this. I mean, so value function approximation, that is Q learning and TD learning. And it's much easier to see. So I won't have any squiggles now. It's very, very easy to show that something very similar happens. That when I want to get an optimal policy, I'll have an expectation of something equals 0. All right? And the easiest one is TD learning. Q learning is magic. It's just genius of this guy Watkins at Cambridge. So this was way less ingenious, but there's an awesome literature on this as well.
He stands for something?
That's the thing. Neither of them really stand for anything. You know, I always joke. I mean, what's a woman's name that starts with a Q? Anybody have one? But it must have been Watkins' girlfriend. I mean, I don't know. A Q is a letter that appears in the algorithm. I mean, how could he be that unimaginative? He must have had a secret reason for the Q. TD is a temporal difference. There's a difference of terms in the algorithm. Can you imagine? I have a minus sign in my algorithm. I'll call it the minus algorithm. It's just, it's wacky. I don't know. I don't get it. So let me explain it. So let's look at the simplest case of solving Poisson's equation. So now instead of, before I had policies, now I have value function approximations. All right, so I've told you that in the case of the belief state business, I told you my value functions are piecewise linear and concave. So I have a lot of intuition. In the speed scaling model, I claimed that a fluid model gives me a lot of intuition. I've got all this intuition, and I can pump it all into my parameterized family, you know? Right? I mean, for the speed scaling model, I know it's been a while, but remember that this was this thing where it was just like a queue, and it cost me, I had an energy cost of speeding up a processor to try to drain the queue whenever it gets big, you know. and there was a cost for the queue getting long. If you go back, we came up with some approximations for the value function, and it was of this form. Okay, there was a fluid value function we could compute exactly, and it was like x to the 3 halves. But that involved some hacking away, and maybe you'd like to correct it with a linear part, or maybe you do something else. All right? All right. So what I'd like to do is find theta 1 and theta 2 to get the best approximation. And remember, Poisson's equation is what? Let me stop here. Why would I suddenly start talking about a fixed policy? Why would I solve Poisson's equation for a fixed policy? Come on, come on. What have been before the bandit? I know the bandits scared all of you away, but before bandits, we were talking about something else. Do you remember what we were talking about before the bandits got in the way? We had linear programming, we had value iteration, and we had policy iteration. So if we're going to try to run policy iteration, and you've got some horrible situation like this robot problem, where my state lives in a triangle, I might try to do policy iteration, but I can't solve Poisson's equation exactly. So instead, I'll opt for an approximation within a finite dimensional class. You know? And again, I know for the belief state, I know it looks concave and piecewise linear, so I've got a really nice class. All right, and remember though, here we did this sort of trick. We said, well, it's not unique. So we said, set h of some x dot equal to eta. So this is the trick I used in order to derive all those algorithms, policy iteration and value iteration, all that stuff. All right, so here are the steps. So what I want to do is I want to derive what's called the TD lambda algorithm, and I'm going to do that for you in the next 6 minutes. Go? Go. All right, so first of all, step 1, interpret this. I'll call it A. All right. When I write pH, all I mean is the conditional expectation of h of xt plus 1 given the history up to time t. All right, and that's what I've got here is I've plugged in x equals x of t here. Anyway, you all better know how to do that. You better know that. Have I forgot a? Yeah. Who cares? I'll call it minus eta then. No, okay, that's good. All right. B. And let's give that a name, right, shall we? Let's call that a temporal difference. And I'm terrified that I got the sign wrong. Let me see. I think that would be minus d. So now you know where the TD comes from. There's a difference of terms, and so we're going to call it a temporal difference. And if I got that, and I think I've got that wrong. No, that would be plus in, hold on 1 second. No, that would be plus. In the standard definition, that would be a plus sign, because in the discounted case is a beta here, and you want this thing to be negative, yeah. I'm just thinking about the language in the textbooks. All right. All right. So B, the expectation of what I just defined times any function zeta t equals 0. Well, not any function. What I've done here is I've multiplied through by function zeta t and brought inside the conditional expectation. When can I justify that? No, I took it inside an expectation. It's random. When can I take it inside a conditional expectation? Come on.
When zeta t is not a function?
It's a function. It's a immeasurable with respect to the past. So it's a function of past observations. It's ft measurable. So, and the thing is, I better make this thing bounded or something. So for any bounded ft measurable function, say, it doesn't have to be bounded. All ft measurable functions for which the expectation makes sense. You know, this expectation has to be meaningful. So the expectation of the absolute value has to be finite or something like that. Okay. What's that? No, got rid of it. No, I mean, if I multiply both sides of this equation by zeta t, you're right, it'd be 0. But I want to get rid of it. You know, and in fact, these are equivalent. So actually, if you go back and look at the definition of conditional expectation as it would be presented in like stochastic methods 1 or 2, the conditional expectation is defined to be a projection. You know, and the fact that, you know, I mean, well, the fact that this is 0 means the dot product. So this is a dot product. The dot product of this and anything that's ft measurable is 0. This is part of the definition of conditional expectation. Okay, so this holds if and only if this holds for all ft for which this is defined. All right.
Getting rid of the like conditional notation is like, is it gone or is it just hidden?
No, it's gone, because the thing is that if this is 0, then the mean is 0 as well. That's called so this implies this is called the smoothing property of conditional expectations. That the expectation of conditional expectation is just the expectation. Okay,
if
so this implies this is always true.
If it's 0, then the expectation in general.
Yeah. The fact that this implies this is actually the definition of the conditional expectation in terms of a projection. Because it's like the dot product of these two guys is 0 for everything in ft. So this implies this is deeper, but it's the core definition. All right? But all we need is this implies this. That's all we need. And then we have this awful, what's called the Galerkin method, and I hate it. And some of you know what that means besides, you know. Okay, so it's a favorite thing of physicists and all. And have you ever seen this? I don't know. Well, yes. It comes up in, what does that stand for again? Proper orbital. Well, it's a way of analyzing it. So, yeah, it's a way of constructing Galerkin and justifying.
Galerkin projection?
What's that? Not project, I mean, it's basically a relaxation. So what you do is this. So if theta is d-dimensional, we only want d constraints. So so if theta is an RD, if I put in too many of these functions, I'm going to make it overconstrained. And so I'm going to have d functions. And all we're going to do is insist on that for those i's. And this we'll assume is in steady state. We'll assume we have a stationary version of the model, so this doesn't depend on time. Right, so xt has distribution pi for all time. It's a, it's a stationary realization, and zeta t is some function of zeta t, of xt. And can I give you the algorithm? Almost there. So td lambda, which we do, let's fix a lambda between 0 and 1. Usually, it would be from 0 to 1 with a hard right on the side. I think that won't work in this average cost case. So I think it should be strictly, I'll get rid of that and make it round. Let's avoid 1 for this particular case. All right? And let's, it's a special case, let's take a linear parameterization. All right. So again, in the speed scaling case, we just had two basis functions. Okay. So that's psi1 of x and that's psi2 of x. All right. And it doesn't have to be a linear parameterization in TD lambda, but I'm just trying to make things simple for this. And zeta t, you just take the basis functions and you put them through a low-pass filter. All right, there you have it. And so, not quite. I need a D. And so what I do is I didn't give myself enough room. I can always just do that. Obviously when I mean d theta, I just mean the same thing with h replaced by theta, h theta. Isn't that awful? Now, I haven't done anything yet, right? Because I'm in the same boat I was before. I'm saying that TD learning, what it does is it motivated by this characterization of the solution to Poisson's equation, cooks up a completely arbitrary Galerkin relaxation and then seeks to solve that equation. But you notice again, I have an expectation of something that involves theta, and I want to solve that, set that equal to 0. In this case where I've got a linear parameterization, this whole thing is linear. I mean, it's trivial. You can go through and solve it by Monte Carlo. It's really trivial, right? I mean, look, this is a linear function of theta. If you go through and you plug in what all this means, you'll get m theta. It becomes trivial in this case. Anyway, it's a linear function of theta. You can figure out how to solve this yourselves. But we want to deal with nonlinear parameterizations as well. So we have to be more clever. All right. So I didn't give you an algorithm. I just gave you what we'd like to solve. All right. And we only have 1 minute left. Shit. It's over at 2:45, isn't it?
Yep.
Damn. I was hoping I'd at least be able to write it down. So the first homework problem, I made you do that silly simulation experiment with the G, and I asked you to figure out which G gave you the best performance. Well, that was involving an expectation just like this. You were trying to find, if you write it down the right way, you were just trying to solve a similar problem. And what we're going to do is just cook up exactly those kinds of algorithms to solve these sorts of problems. And we're going to find they don't work. They don't work on such a dramatically, they fail so amazingly you won't believe it. And I was trying to, that simulation experiment you were doing was meant to sort of give you early warning of that. That if you don't come up with a simulation-based method for solving this carefully, it'll take forever to converge. So what we're going to have to do is, I'm going to feed you some stochastic approximation theory while we develop this. And I'll hold off on most of the theory. So we'll do most of the algorithm design over the next weeks, and get into the stochastic approximation theory as we go. So next time, I will tell you what stochastic approximation is and give you hints at what's dangerous. And we will do all these algorithms. We can do TD learning and Q learning, explain how they're derived in the same way, and knock those off, and then go on with that. Yeah, all right. So, any of you who didn't have your exam, I've got it with me.